This video is on the objective determine the p-value for a hypothesis test for the mean, but this time with the population standard deviation unknown. Okay, so sigma is unknown, meaning that when we do a hypothesis test for the mean or about mu, it's going to be a t-test. Our test statistic will be a t-score, and we'll be working with the student's t-distribution with so many degrees of freedom. And this is number one, right? So the first video related to a question on this objective from your Newton-Alta homework. So let's take a look. So again, if you're unfamiliar with the topic, want to see more about what they're doing, click on More Instruction and look at their videos, their notes, their examples, and hopefully those help you. Alright, so let's read through this. A newspaper reports that the average annual salary of a full-time college professor in a certain region is $127,000. Scott, a statistics major, wants to test this claim that the average annual salary of a full-time college professor, all the college professors in some region, is $127,000. He selects a random sample of 75 full-time college professors in that region. The following is the data from this study. So remember, the null hypothesis would be that the mean is $127,000. So that's the claim, right, that the mean is $127,000. Then the alternative hypothesis here is the opposite of that, right, that the mean is not $127,000. And if you remember, when the parameter is not equal to some value in the alternative hypothesis, then this is a two-tailed test. All right, and if it's a two-tailed test, our p-value, right, remember the p-value for a test statistic is going to be either the value to the left doubled or the value to the right, the area to the right doubled. It depends on which side of the mean you are, which side of the middle, and we'll see that coming up here. All right, so the sample mean salary for the 75 college professors is $126,092. The sample standard deviation was $8,509, and they've already calculated the test statistic for us. They took 126,092, subtracted 127,000, then divided that by s over the square root of n. They divided that by 8,509 divided by the square root of 75 and got negative 0.92. Alright, so this particular sample mean is 0.92 standard deviations below 127,000. Now the question is that too far away? Is that relatively small, relatively far away from the middle, so that I wouldn't accept the null hypothesis? I wouldn't accept a mean of $127,000, or is it relatively close to the middle? And then I would accept the mean being $120,000. I wouldn't reject the null hypothesis. Well, that's where the p-value is going to come in this time, right? Again, there's a critical value approach, and then this p-value approach. All right, so I'm going to go to a piece of paper here, and we'll talk about calculating p-value. So again, we're working with a student's t-distribution this time, right? So my horizontal line, and it's a student's t, right? My sample means here, my sample means by the central limit theorem would be a student's t-distribution with, now remember the sample size was 75, right? So they took a random sample of 75 full-time college professors from this region. So the number of degrees of freedom would be, one less than that. Right? Remember, 74 degrees of freedom. So I'm looking at this student's t-distribution with 74 degrees of freedom. Right? Remember, it's pretty similar to the standard normal distribution, right? Bell-shaped, symmetrical. Only the numbers on the horizontal axis here are t-scores instead of z-scores. And underneath the peak is a t-score of 0. Right? A t-score of 0. Now they told us, what our test statistic was, right? The test statistic is negative 0.92. So I'll mark that off here, negative 0.92. Right, there's the test statistic, right, test stat. Now, that is clearly to the left of the mean, right, the left of the middle. So when I'm talking p-value, now remember I told you this is a two-tailed test, right? The alternative hypothesis was this. It was that the mean was not $127,000, the mean salary for professors in this region. So that's a two-tailed test. And you might recall, from the p-value approach when we did z-scores instead of t-scores, it's still the same calculated the same way. In a two-tailed test, the p-value in this particular case, right, is going to be the since my test statistic is left of center, it's going to be the area to the left doubled. So twice the area to the left of my test statistic. Now, you got to be careful, right? If the test statistic were to the right, you'd take twice the area to the right of the test statistic, right? So just pay attention to which side of the middle you're on. All right, so now you can find this area, from a table. Or from your calculator. Alright, so the table is a little trickier. What I'm going to show you is, I'll do it on the calculator real quick. So remember on a calculator, if you want the area under a t curve, or a student's t distribution, you find it in the same place that you would the normal distribution areas. Remember normal CDF was for area under a normal curve? If I scroll down a little bit more, number 6 is TCDF. That's going to help me find the area under a student's T curve. Alright, and it's kind of set up the same as the normal stuff. Trying to find this area to the left of my test statistic. What's the lower value? Well, there is none. Right? It's all the way to the left. So I'm going to put in some big negative number, like negative and then 5 nines or something. Something that's clearly left, far away from the middle on the left. And then what's the upper value in this region? Well, that's my test statistic, negative 0.92. And then how many degrees of freedom? Mentioned that. That was 74 degrees of freedom. Okay, so this is the area to the left of my test statistic under this t distribution curve. The area is approximately 18%, 0.18. So then the p-value for our test statistic, again, because it's a two-tailed test, is double this. Right, so I just go times 2, 0.3. It's about 36%. Right, 0.36. There's the p-value, rounded to 2 decimal places. And then remember how you make decisions. You compare p-value to alpha. Now, a particular value of alpha, right, the significance level, was not mentioned in this question. If that's the case, you can assume that alpha is 5% in most tests. That's pretty reasonable. But all we're talking about is p-value here. So there's one way I can find the p-value is with the calculator. It's 0.36. That's pretty big. All right. So because that's really large, I'm going to say that's definitely bigger than 5%, right? I would not reject the null hypothesis, right? Remember, if the p-value is greater than alpha, you don't reject the null hypothesis. If the p-value is less than or equal to alpha, that's when you reject the null hypothesis. But again, we're not asked to do that here. Now, what we are asked to do is use this table to help us determine what values, the p-value will be in between. All right. Now, remember, it was 74 degrees of freedom. All right, 74 degrees of freedom. So I'm looking at this last row. Now the test statistic was negative 0.92. These are using positive scores here. So let's take a look at what let's use positive 0.92 just so I can compare them to these values. And then this probability is, like the area to the right, the area above these are like critical values. Right? All these values in the heart of the table are critical values with certain areas above them. So you see for a t distribution with 74 degrees of freedom, the t-score of 1.293 has 10% above it. The t-score of 1.666 has 5% above it, and so on. Well, 0.92, right? 0.92 is definitely less than this. So that means a t-score of 0.92 has more than 10% above it. Right? So the p-value would definitely be more than 10%, if not more than 20%, because you'd be doubling. All right. This is just right tail areas. So let's look down here. So that, the probability of observing this test statistic or less, or observing 0.92 or more, right? The two tails. When you look at two-tailed tests, I look at negative 0.92 or less, and the doubling is kind of like looking at the positive 0.92 or more. You look at the left tail and the right tail. So the probability of observing this or less or that or more, if the null hypothesis is true, is between 10 and 20%. No, it's not. Remember, I told you it's more than, definitely more than 10%, which if you double will be more than 20%. So the probability of observing this or less, that or more, is, if the null hypothesis is true, is greater than 20%? Yeah. All right, because again, looking at this table, a score of 0.92, a score of 0.92 with 74 degrees of freedom has more than 10% above it. So that means a score of negative 0.92 would have more than 10% below it, and both of them together, put together, would have more than 20%. All right, so this second statement is true. And yeah, no, not this one. And this one's just a one-tailed test. This one would just be a one-tailed test. So, we're dealing with a two-tailed test here, so you gotta look at the positive side and the negative side. So it's got to be that second statement. Right. Okay. So again, that was a little trickier because of the table stuff, but you could have also figured that out with the calculator, figured that the p-value would be greater than 20%. Right? And we saw when I used the calculator a minute ago, the p-value for our test statistic there was 36%, definitely greater than 20%. Right. And I believe that's all. I think that's all that this particular question had in mind. Yep. Okay, so hopefully watching me do this one, and I'll have another one coming up as well, helps you when you're working on this kind of problem on your own. And thanks for watching.